Okay, so I'll be talking about minimal sufficient explanations for factored MDPs. This is joint work with Pascal Poupart and Jay Black from the University of Waterloo. I don't think I need to go over the motivation for this audience of why sequential decision making is an important area because it has lots of applications. I'll just point out some difficulties that we face in it. So there could be uncertain action effects, especially if it's a stochastic domain. You could have multiple objectives that you want to satisfy. And it's, for instance, it's sequential, so you have to make decisions repeatedly. So what can you do? You can harness the power of machines. You can generate policies automatically using frameworks such as Markov decision processes. But then the issue becomes, how would someone who is getting that policy trust that policy? And how would someone who's designing the model verify that the model is leading to the correct optimal policy? So the contribution of this work is going to be on policy explanation, so that can help you in trusting the model or trying to validate whether it's doing the correct thing or not. I'll briefly go over some background about MDPs. I'm assuming lots of people over here already know about that. Then I'll talk about how we can generate explanations automatically. I'll report some results from some experiments I conducted and give some sample explanations. I'll also describe a user study that I conducted for these explanations, and I'll conclude with some future work. So this is how you can represent an MDP graphically. You have a set of states and a set of actions. So in a particular state, if you execute an action, you have a probability distribution of reaching another state. So that's described by a transition function. And whenever you execute an action in a given state, there's also a reward associated with that, and that's provided using a reward function. So this is how we represent an MDP, and now the goal is to compute a policy which maximizes the expected total rewards. So this is, it's not going to be easy to understand this figure, so just follow what I'm saying, and that's all you need to take away from this figure. So this is my running example for the rest of the talk. I'm using MDPs to compute policies for a course advising domain. So undergrad students have to take elective courses that they should take in their upper years. So what I'm using is a system over here which recommends this is the action, where the action means picking a set of courses or a pair of courses. So each course, the transition model in this domain depends on historical data. So we have data from previous students, and through that we can figure out which students who had grades in different courses were able to, what grades they were able to get in the new courses. And the reward function over here depends on the objectives of the student, which is to complete the degree. That's what I consider right now. And to complete a degree over here, we assume that you need to complete 6 elective courses, and you need to cover 3 different areas. So each course belongs to 3 different areas. So the representation, so this is a 1 time slice or 2 time slice deviant representation for that MDP. Now, how do you compute an optimal policy? So there are many techniques. You can use value iteration, and this is a well-known equation that most of you would know. So the value of a policy is the immediate reward you get, and then all the discounted expected future rewards. So R of SA is the immediate reward, and it's a recursive definition. So whatever state you can reach from that state, and then the rewards you can get in the value of executing the policy from there on. So that's the traditional way of computing an optimal policy. What I'll do is I'll present an alternate representation for the same approach. Now you can also use occupancy frequencies. Occupancy frequency is the expected number of times you'll visit a state, given a starting state and a policy. So the equation for computing occupancy frequencies is shown over here. And it's similar to the equation you had above, but now what you're doing is the first part of the equation just tells you whether you're already in that state or not, and the second part then tells you, so if you reach another state, what's the probability of reaching your desired state from that point? And if you have these occupancy frequencies, then you can compute the value of a policy through a different way where you multiply the rewards with the occupancy frequencies of those states. So that also gives you the value of a policy. And this is the representation that I'll use when formulating my explanations. So as you saw from the previous slide, it's policies are computed using complex numerical techniques. So, and that's why we also want to explain these policies. And now the very basic explanation is that the optimal action is maximizing the total expected reward. But that doesn't tell you much, right? So what does it mean if it says that if you take these two courses, your expected reward is being maximized? In addition to that, there could be many factors which are contributing to that utility. So there could be some utility associated with completing different courses or covering different areas or having high grades in those areas. On top of that, having a numerical utility is not always going to make sense to a user. Not for a designer, it's okay, but for a person who's going to use that policy, it may not be useful to say that, okay, if you complete 6 courses, you'll get a reward of 100. That 100 doesn't have any unit for that person. It's just a utility. So we don't want to use that either in the explanation. So what do? We use predefined templates, and these templates are populated at runtime. The reason behind using templates is that we don't want to go into natural language generation, so we'll just have a fixed template and we'll insert values in them at runtime. And also the number of templates shouldn't be very large. We want a few templates so that the explanation is understandable. The information which is filled in these templates is about the occupancy frequencies of different states. So if a state has a high or low reward, we report that occupancy in the template, but we don't report numeric utilities. I'll give you a sample explanation later, but this is how a template would look like. So the values which are underlined and bold, they are the ones which are being filled, and the rest of the template remains the same. So if you look at T1, it says action, and over there you fill whatever the optimal action is for that state. Is the only action that is likely to take you to, and now over here you have a state, so whatever that state is, about x times, where x is the occupancy frequency now, which is higher or it could be lower than any other action. And then I have similar templates which, if it's not the highest or lowest, then you have other variants of this template that can be used as well. Now, if you look at those templates, it's possible to generate multiple templates even for non-optimal actions, because the template is just telling you that in this, if you're in this state and you execute this action, this is the number of times you'll reach a particular state. So that's not really telling you anything about the optimality. So even if you consider a non-optimal action, it may have the highest occupancy frequency for a particular state with high reward. That's still possible. So if you have just one template, that's insufficient. If you use too many templates, then it's going to be complicated for someone to understand that explanation. So our goal is to identify a minimal subset of templates that are still sufficient as an explanation. Before I explain how we compute a minimal sufficient explanation, let me just go over with you a small definition about what's the value of an explanation. So a template, as you recall, is the expected number of times you reach a state, which is the occupancy frequency, which is represented by lambda over here. And then you have a state, that state has a certain reward associated with it as well. So if you follow the policy from there on, what's the reward for that state? So that's represented by R over here. So to compute the value of an explanation, we have this product of reward and frequencies for those templates which are being inserted in the explanation. And for the rest of them, we have a component which is, so what we're saying is we don't need the rest of those products, right? So what we assume is no matter what happens, this action is still going to be optimal. So we consider the worst case for those states, which is the minimum possible reward for those states you can get. Now, how do I get a minimal sufficient explanation? An optimal value policy has the highest value, so that's the leftmost expression on leftmost part of that expression, V pi of star. And that value has to be greater than every other policy, and that because it's an optimal policy. So the value of that policy is going to be greater than any other policy. So V pi star is going to be greater than any other V pi prime. Now, what we want is the value of our explanation to lie in between, so that we can remove some of those products in the upper line, and still have the explanation. Listen, the explanation has a higher value. So that's the objective over here. And that's how we compute minimal sufficient explanations. One thing which you may note over here is that in the first equation, the summation is over all possible states. So for every state, you need to have these factors. If you're talking about some real-world MDPs, these states could be in hundreds of thousands or millions. So this formulation, as it is, it's not going to yield a good. Even if you compute a minimal sufficient explanation, it's not going to be understandable. So what we're looking at are factored MDPs, And one of the reasons is that if you have a very large MDP, typically you specify it in a factored manner as well, because not every variable contributes to everything. So you only so when you define the transition function or the reward function, you have different factors. So for factored MDPs, the state space is defined by a set of variables. Each variable is assigned a value, and together it's considered a state. But now we can also define a notion of scenarios. So a scenario is a set of variables being assigned values. So it's a partial assignment, and we don't care about the values of the rest of the variables. So a scenario essentially becomes a set of states. So that's how you can use now these scenarios to define your transition functions and reward functions. And the value of the policy now can be computed using this scenario. So over here now you see that we have two summations instead of one now, and that's because the reward function could be decomposed as well. So the first K is over the total possible reward variables, and then the R is for every value of that reward variable. And SC is now those scenarios which have value R of reward variable capital R. So you can compute the value of the policy and explanation using this technique as well. So for explanations, it's going to be very, very similar. And now what you're doing is you're doing the same thing, but using scenarios instead of states. And the hope is that the structure in your problem is going to reduce the number of templates that you're going to use in the explanation. We know that if the reward function is scaled by any constant, if you add or subtract any constant or you multiply it by a positive constant, the optimal policy won't change for an MDP. So we want that property for our explanations as well, that if you scale up or down the reward function, the explanation for the policy should remain the same. And the reason for that is if it doesn't, then that's going to confuse the designer who's trying to look at the explanation and figure out what's wrong with the model. So if the model is the same, then the explanation should also remain the same. So I have a very small, it's easy to show that, and I show that in the paper that these explanations are invariant to those transformations to a reward function. The algorithm for computing minimal sufficient explanations basically revolves around computing occupancy frequencies. But before that, what you need to do is you need to compute, so occupancy frequencies are for different scenarios. So first of all, you need to compute those scenarios. So for every reward variable, so that's the outer loop, and the inner loop is for every value of that reward variable, you compute those scenarios. So those scenarios in which you get that value, small r value of the reward variable r. You compute its occupancy frequency, and then you compute the product of the occupancy frequency with the reward, and along with it, the product with the minimum possible value for that reward variable as well. I'll get to that in the next slide, why is this important. Now, the benefit of including this term in the explanation is basically the term minus the interim value. So that tells you that if you include the explanation, this is the benefit, and if you exclude it, this is what you're getting, because that's the portion which gets added to the value of the explanation. Once you have that, you can sort these values, and then you can pick keep on picking templates, sort them in descending order, and then keep on picking templates until you get a sufficient number of templates such that this equation gets satisfied. So it's going to be easier if I go through a very simple example for you. So recall that we have a course advising domain. There are two objectives. One is to complete 6 different courses, elective courses. And you also want to cover 3 different areas. So you have different rewards. So R1 is about covering 6 courses. R2 is about covering 3 areas. And as you can see, these are scenarios now. It's not a state. So it could be any set of any state which leads you to completing 6 courses or leads you to covering 3 areas. And then for the optimal action, in the first line, you have the occupancy frequency for reaching a scenario where course is 6, or the scenario where you don't complete 6 courses. And you also have the product in the subsequent line. The optimal, the value of the optimal policy is simply the sum of all these together. So you can see it over here. Now, we also have other actions. So if you consider some other action pi prime, you can also compute the value of the policy of pi prime, which we do over here. So this is again just simply adding the products of rewards and occupancy frequencies. Now, if you want to compute an explanation, in this case, as I mentioned, you also have a product of the occupancy frequency of a state with the minimum possible value of that reward. So that means if you're not including that scenario in your explanation, so that means you're assuming the worst case for it, which could be having the minimum possible reward. And this is important because the rewards could be negative, and if they're negative, then just having the sum of the terms which are in the explanation, that's not going to be correct. Otherwise, even if they're between 0 and 1, or if they're not non-negative, even then, if you want a precise computation of the sufficiency constraint, you still need this. And if you go through this now, you only need the third term, which is telling you that you can reach the scenario with 3 areas covered with probability 0.95 of the times. So if you do that, the value of this explanation is going to be higher than the value of the next best policy. And that's why if you look at the value, it's 84.5. So the way you get it is you have the value of the term in the explanation, which is 95, and then you add the minimum possible values for all the other areas, so which are minus 6.7, minus 3.3, and minus 0.5. So if this value is greater than the next best policy, well and good. If it's not, you go back and add whatever is the next best one. So if it weren't in this case, then we would have added the first term, because the benefit of adding that term is 73, so which is the second highest benefit. So keep on adding them until you get satisfy the inequality. I ran some experiments using this technique for 2 different domains. The first one was the course advising domain, which I've already described. This domain has around more than 100 million states, and there were 21 actions. It's a finite horizon domain. There are only 3 steps. So it's simulating 3 different terms, the last 3 terms of an undergrad student. There's no discounting taking place. We generate a transition model from historical data, and the reward function is specified by the degree requirements. The other domain that I'm using is the hand-washing domain. So this is from Jesse Hui and his collaborators. So they use a POMDP. I convert it into an MDP, and then I use the same model as whatever they're doing. And the converted model has 200,000 states, almost 25 actions. The horizon is 100, and there is some discounting in that domain as well. So sample explanations is one sample explanation from each of those domains. So to understand the explanation, you need to know something about the domain. Or like in the first one, the action is take CS343 and CS448. So it's telling you to take 2 different courses. And it's saying it's the best because it's likely to take you to, then it's giving you a scenario, which is courses completed is equal to 6 and term number is final. So by the end of the last term, you would have completed 6 courses, which is one of the degree requirements. About 0.86 times, which is as high as any other action. So that's one example of a minimal sufficient explanation. Second explanation is from the hand-washing domain. So over here, it's saying the best action right now is to do nothing, which it's underlined over there. And the reason for that is it's likely to take you to the state where hands are washed, yes. So that indicates the scenario in which the person has successfully washed hands and they are clean and dry. About 0.71 times, and the second, it also needs a second template to be a minimal sufficient explanation. And the second one tells you that prompt is equal to no prompt. So prompt is an action. So what prompt should we issue to assist the person with dementia and hand washing? So it's saying that you don't need to issue any prompt over here. About 12.71 times. So this is a good thing because we don't want to issue prompts all the time because we want. So this domain was basically for people with dementia who have trouble in everyday tasks. So the authors didn't want the system to guide the person all along. So they wanted the person to act autonomously if they could. If the person had trouble, only then intervene. So it's saying that it doesn't intervene all the time as well. Now, the concern was how many templates would we need in the explanation. So the number of templates we need is dictated by the number of different values for the reward function. So we're assuming the reward function and transition function are discrete, obviously. In the course advising domain, since it's a simpler reward structure, it only has 4 values. So 2 for completing course requirements and the other 2 for completing area requirements. And most of the times we only needed 1 template, at times we needed 2. For the hand washing domain, the reward function was a bit more complicated. It had 19 different possible reward values. So for this case, we needed templates between 1 and 6, depending on different states. One thing which I would like to point out over here is that intuitively you would think that if 2 policies are close, or if a state is more difficult, then you would need more terms to explain it. So that somehow bears out over here as well. So if you look at the last row in both tables, that's the ratio between the next best policy and the optimal policy. So when this ratio is low, you need fewer terms. But as this ratio increases, you need more terms over here. This is more clear in the second table. So as the mean ratio increases, you need more terms. So that seems in line with our intuition as well. After running these experiments, I also wanted to conduct a user study so that I could get a sense of whether people who would actually use explanations would find them useful or not. So I recruited volunteers from our undergrad department. I've got 37 undergrad students to come in and have a look at these explanations. I showed them 3 explanations each, and after showing them those explanations, I also showed them 2 explanations that are already provided to them by human advisors as well. So this is what they would be initially shown. So this is a state of the student. So it's saying that what courses the student has covered, what courses the student has not covered right now. So the electives are the courses which the student can take if he has not already taken them. And now we ask the student, tell the student, okay, that this is, here's an optimal action for you, and this is the explanation. Like we'll say, okay, take 343 and 370 for this scenario. And the reason why we are recommending this action is the following. So we asked them to evaluate this explanation. What the gist of the results are that most of them found it easy to understand. They said it provided extra information, and they seemed accurate as well. But they also said they needed more information in the explanation. So the last column says that 77 out of 130. So since each student was shown 37 explanations, so there's a total of 111 explanations which were shown. Out of which, so 77 times the students said that they wanted more information in the explanation. So we asked, there was then a free text box for them as well to respond to what kind of information they wanted. And most of the students said it's not reflecting their preferences, like whether the courses are in the area they want to, or the courses are going to help them in a particular career path or stuff like that. But that's not information we're modeling. So that was fine, because if you include that information in the model, then we can include that in the explanation as well. The other concern, so I think that's more related to the students being CS students, it was that they wanted to know more information about the model. They said, how are you computing the explanation? So we want, or how are you computing the recommendation? We want information about that in the explanation as well. What was the size of the data set that you used to compute the explanations? So I don't anticipate people from other domains having such kind of questions. Then the second part was, so this was a somewhat unfair comparison for our explanation. So comparing our automatically generated explanations with explanations generated by advisors. So again, the explanations shown by advisors were something like, if you take 3 databases, that's going to help you because you've already taken these courses, so you'll have a strong background in that area, and then you'll be able to go and find a job in that area. Or they could be, okay, since your goal is to go to grad school, you might as well take algorithms, because most of the time you need a strong foundation if you want to get accepted in a grad school for that. So those were the types of explanations advisors were giving. So we didn't expect our explanations to be better in any case, but the interesting result over here was most of the students said that if we combine the 2 explanations, ours and the ones by advisors, so because they both complement each other, that would be a better fit as compared to either one on its own. So that was encouraging, because what we're doing is we're giving them quantitative information, and what the advisors are giving us is more subjective. And one thing which is obvious was that our explanations wouldn't have been easier to understand, and that shows in the last box that only 1 out of 37 said ours is easier as compared to an advisor. So that's obvious. We're using a template, and it's not an interactive explanation either. So in conclusion, what I've shown is a domain-independent technique of generating explanations. It doesn't require, so it's domain-independent because it's populating templates at runtime. We don't use the numerical values of utilities, and we compute a minimal set of explanations which we think should be sufficient to explain why an action is optimal. One important goal we had was that there shouldn't be any additional burden imposed on the designer of the MDP. So the technique works as is with any existing MDP that you can pick up. And the user study also indicated some benefits of this explanation. That's it. Right, right.
So it's kind of hard to know, what's the value of that user study, what you draw from it.
So I think that, so this particular point that you're pointing out, so it's a difference between understanding what the system is doing and the other is believing that the system is doing the correct thing. So I think the effect, what's happening over here is that what we're telling the students is we're giving them some quantitative information. They don't fully understand how that information is going to lead them to the goal, but it makes some sort of sense to them. So they say, okay, if it's giving me this, so that what it's doing might be right, rather than just saying, okay, do this. So that's how I would interpret it.
So it seems to me that you're generating explanations for different kinds of users.
Right.
At one point, you might be generating explanations for modelers who are trying to understand and debug their model. And at another point, you'd be explaining what the decisions of the model have been for users. And it seems to me that this kind of thing is more useful for the modeler, where the underlying framework of the model is already understood by the user, the person who's trying to understand the explanation.
Yeah, that's true.
Whereas, I mean, in the other case, it seems that very often people want explanations because they have misconceptions about basic questions that are being asked. And your system really doesn't deal with that. I mean, you can't, for example, say, well, the reason you shouldn't do this course is because actually you failed that course, and that means you're really a disaster at that area of the subject. This doesn't really come up with an explanation like that.
Right. So it's not going to say that explicitly. And maybe that's a good reason as well. You don't want to dishearten students. But I understand what the point you're making. But it's being considered implicitly in the sense that the transition model is taking that into account, that the student failed that course. So that's why if he takes this course, he's not likely to maybe pass the next one. And if he doesn't pass the next one, he won't be able to complete the objective of completing the courses. So it's saying that if you take this course, you're not likely to finish your courses. Right. So on top of that, you can then have, so this was the first, answering the first why of the student. On top of that, you could say, okay, the student could again ask, okay, why is this the right occupancy frequency, right? So because why am I not likely to finish courses if I take this action, right? Why is this the low number? And that's a problem of then explaining the inference, because the transition occupancy frequency, the way it's computed is basically variable elimination using algebraic Gaussian diagrams. So it's similar to what you do, how you would explain a query for a Bayesian network, right? You would have, or a dynamic Bayesian network, that you would say that, why is this node going to have this probability? So that's second level explanation and we haven't looked at that right now.
So I'm trying to figure out how if you could turn this into a query-driven thing. So why didn't you tell me to take that class?
Right.
I mean, it seems like you should be able to find the places
right.
where.
So initially when we designed the system, we didn't have that facility, but after the user study, lots of students said we wanted, so if I want to take some other course, why not let me take that and tell me why that's a bad choice for me? And it's a legitimate reason that lots of people would have something else in mind, and that's why they would be questioning the system. And they would want to know how their approach compares to this particular action. So let's assume that student wanted to take the action which is given by the policy pi prime over here. So now what you could do is you could do the reverse of what we're doing already. So what you could do is you could again compute the interim and benefit terms over here. And now you would be taking those terms which have the minimum values instead of having the ones which have the highest values. And including them in the explanation that you're doing so bad on these terms that you don't care what happens in the rest of the cases. So just that portion is sufficient to tell you that this is why the other action is better than the one that you were asking about.